All right. Well, good morning, everybody. This is Jomo Stewart and Jim Dotson and Roger Burgraff here at the Fairbanks Economic Development Corporation. It is Tuesday, June the 8th, 8:07 in the a.m., and we are here for the Energy for All Alaska Task Force meeting. Our guests this morning are, we have Doc from ACEP, as well as a couple of gentlemen from Westinghouse, who will be giving a presentation regarding micro-nuclear. Of course, you know, I actually am from Virginia. In my hometown, right across the river, was the Surrey nuclear power plant, and it is huge. But of course, we know that nuclear reactors have been fairly compartmentalized and transportable for some time because the Navy's been using them for decades. But now it's starting to move into the commercial sector. So, gentlemen, please, the floor is yours. If you'd introduce yourself.
Sure. Yeah, we can. Go ahead, Mike.
So I'm Mike Valor, and just thanks everyone for having us today. I really appreciate the opportunity to be here. I'm the Senior Director for Advanced Reactor Commercialization with Westinghouse. I've been with Westinghouse for about a dozen years. Prior to that, I worked in supercritical coal plants, huge ones, 2,700 megawatt size plants. Really got to see firsthand what fossil energy was really about, and wanted to move into more clean energy generation. In Westinghouse, we were about a dozen years ago, we were really heavily into moving forward on our AP1000 projects in China and in the U.S. So I joined into the engineering organization. From there, led some of the projects of where, some of our key challenges on AP1000 in the early days. And then the past 6 years, I was responsible for delivering all the material and equipment to the China and the US AP1000 sites. So everything from the rebar and even stuff like concrete aggregate and things like that, the whole way to the reactor plant equipment. Three of those 6 years, I actually led our Westinghouse global North American, I should say, supply chain, even though we did most of our supply out of North America. And then I got an opportunity to move back into advanced, kind of the next technology, which is why I came to Westinghouse in the first place. So I've been in this role for about probably 8 or 9 months now.
Great. Yep. My name is Mike Shacko. I'm the Senior VP for Advanced Reactor Program with Westinghouse. It's glad actually to get Mike, one of my key leaders that we got to join the team. We put the organization together back in September. The company had realized after coming back, just bankruptcy. Westinghouse was in a bankruptcy issue back 2 years ago. When it came out of bankruptcy, realized the business is strong with operating plants, Surrey, North Anna. I'm sure those familiar names to you. Those are Westinghouse designed reactors and been operating for many years and safely. But the company realized that, look, even though the fuel, we make the fuel, right, the nuclear fuel, as well as we service the operating plants, as well as we provide the engineering and the support for regulatory type interfaces that nuclear operating plants around the world, and Mike will talk about that a little bit, that we basically have over half of the nuclear plants not designed by Russia or China are actually Westinghouse-based technology. So we provide that kind of support. Anyway, so the company came back and realized that to continue to sustain this business, we got to start looking beyond existing customers, existing base, and we really need to be thinking 5, 10, 20 years down the road, because as the world goes into decarbonization initiatives, certainly the US and many other countries are leading in that area, is that the demand for clean energy is going to continue to grow. And we believe, because we certainly drank the Kool-Aid on nuclear being a safe and clean energy source, we believe that this is the way where we can help from a social economic perspective. Anyway, I've been with Westinghouse for 30 years, left for a few years to go to TerraPower out of Seattle to support the deployment of a plant in China. And that lasted about 3 years. Then I returned back to Westinghouse in September to start the advanced reactor program for the company. We have a team about, on eVinci only, we have about 80 to 100 people working on it. We are in the development stage, and meaning the design and the testing activities in the early stage of the program. In addition to eVinci, we do have other advanced reactor programs that we're working on. One is with the United Kingdom. We recently received a grant from the UK government to advance the development of SMR, bigger, it's a 400 megawatt electric type reactor, generation 4, 2030 plus timeframe. And also we're working with the French Electricité de France, EDF, on exploring opportunities to do joint SMR development with them between Westinghouse and France. So anyway, that's in our portfolio of advanced reactors, and we're glad to be here and really appreciate you guys letting us come here and talk to you. So looking forward for the dialogue. We're here to learn, honestly. I mean, there's very little that we know about Alaska, so we're here, Mike and I talked about on the plane is I'm so eager to learn about the dynamics and what's going on here and the interest and to see if eVinci could potentially help in serving a certain need that Alaska may have. So,
if I may, if I can start, you mentioned SMR twice.
mm-hmm.
What is that acronym for?
Sorry, yeah, it's a small modular reactor. That's an industry lingo terminology. They use SMR for anything that's around 300, 350 megawatt electric. You heard Mark talk about AP1000. It's 1,000 megawatt electric. This is the only nuclear plant being built in the US, just outside Augusta, Georgia. And Mike and I spent many of our years serving the Georgia Power and Southern Company. And the plant is close to being commissioned, going online by end of this year. So.
Okay, so we're talking, so again, the Surrey would be the mega scale plant,
Sarah would
classic
be
industrial,
right.
SMR, small to medium reactor, small modular reactor would say be the 300 to 400 megawatt.
Right.
Okay.
In a micro reactor like us, typically there is no real definition, but we're coming up with our own. So anything less than 20 to 15 megawatt electric, we're calling that a micro reactor.
Okay. Just so everybody has a sense of scale.
Right.
Okay.
Now we're talking megawatt electric, not thermal. Yeah.
Okay. All right. Well, Mike, if you would.
Sure.
Are you able to share your screen?
I think so. Once I'm actually successfully on Zoom, I've never had any problems with it.
Can I just get a verbal acknowledgement that we are all seeing the screen?
Yes.
You're all on mute.
Yeah.
There you are. Thanks, Gary.
Fantastic, Jomo. Thank you.
All right. Thank you.
All right. So just, I won't spend too much time on our history, but, the Westinghouse that Mike and I are part of goes back the whole way to George Westinghouse in the 1800s. From a nuclear perspective, Westinghouse Electric, we were the designers of those, the nuclear Navy reactors, right? So, our history goes back, the whole way to the nuclear Navy reactors, the original ones, and also what's in the fleet now. To also the first commercial reactor, which was right outside of Pittsburgh in 1957. As Mike mentioned, our PWR, pressurized water reactor technology of the big plants is really the leading technology for the existing reactor fleet in the Western world, and even a lot of the Eastern world of China, or I should say Japan and Korea. So Westinghouse's PWR technology, we license to those countries, we license to France. So the French reactors are substantially all Westinghouse technology as well. GE has probably that other maybe 30 to 40% of the Western world reactor fleet with BWR technology, which is also existing in Japan. But we service these plants. We provide fuel. We provide instrument control, cybersecurity. Basically all of the types of services and equipment and things that you can imagine we provide to these existing plants. And that really helps us to really have the stable of people that are truly necessary to develop a new reactor technology. So, from a manufacturing perspective and also just the human capital perspective, we have probably the largest and most capable organization, I'd say in the United States for nuclear. Certainly. 9,000 employees. Some of the competitors in the micro-reactor space, they're really startup type companies with pretty limited resource availability. As Mike mentioned, we have anywhere from 80 to 100 people working on eVinci in a given moment, our micro-reactor. But they're also spread across all the different types of disciplines that we have within Westinghouse and need to develop this type of technology. And we can draw upon that, basically that entire 9,000 employee workforce for any specific, need we may have at any given time. Present in 19 countries just for physical offices, but we actually work in more countries than that. So what is our microreactor? So we call it eVinci. I put 4.5 megawatt electric, but it's really anywhere from 4 to even maybe 5.3 or 5.4 megawatt electric. It's somewhat dependent on ambient temperature. Colder is better. So, we can actually, in some of the areas in Alaska and northern Canada, we can probably push that 5.3 or 5.4 megawatts electric. And that's most power conversion systems are perform better with that big delta T for ambient temperature, but ours is fairly sensitive to that as we're using an open air Brayton type power conversion process. Our reactor is transportable, and I'll talk a bit about that. It's what we see as truly the key differentiator of this technology, even versus other microreactors that are out there right now. We have been doing a lot of cost analysis on this reactor and its associated components and operational costs. We have, I think, a very good handle on the costs of this technology because we've actually been building piece parts. So, there's many of the components we know what the cost will be, and I'll show that a little bit about that today. On-site personnel. We see the need to have one operator on site 24 hours a day, really only from a regulatory perspective. This technology will run itself. It's truly an autonomously controlled technology. Westinghouse has great expertise in nuclear instrument and controls, and it's actually quite a simple device to control. From a security perspective, there's an existing security force at a mine site or a DoD type facility, we don't see any additional security need. But if we were in a community that didn't really have a police force or other response force, we may need some security resources on site. Show a bit about what we've been doing with the technology and manufacturing in just a bit. But, we can co-generate both electricity and heat, which I think is going to be very important in Alaska. And even based on some of the discussions we had with University of Fairbanks and Golden Valley Electric yesterday, we actually got even better understanding of some of the district heating needs and things at the DoD facilities, as well as the town of Fairbanks itself. We can load follow quite quickly. Where we are supporting an off-grid location, we can actually get to millisecond range type load following, multiple megawatts. So we can scale up and down extremely fast, which was basically required for an off-grid type location. But even in some of the discussion yesterday, where we may be able to provide regulation to the grid to support renewables and other things, we can really support quite quick load following. But a great way to think about this really is it's more like a battery technology that you can control how you discharge it. and it discharges its energy in the form of heat. And it's a question of what do you do with that heat, right? And you can do many things, right? We can make electricity, we can generate nothing but heat for district heating, or even for industrial, high temperature industrial processes. There might even be certain situations where we don't generate any electricity at all with this technology. So it really is it's a battery that has about a 5-year life before it needs recharged or refueled. And all of that takes place off-site, and I'll talk a little bit about that.
Just as a reminder to everyone who's online, we do have the chat line open if you have any questions, but as always, you may just simply take yourself off mute and fire away.
Yeah,
Okay,
absolutely. Interruptions are encouraged. As Mike mentioned, we're really here to understand also, we're not here just to present a thing. We want to understand, what reactions you guys have, questions, even some of the questions in the discussion with UAF yesterday really led us to think about some different applications and different ways the technology might be used that we're not really used to thinking about. As Mike mentioned, we're usually more of the big 1,000-megawatt power plant, and you put out electricity on the grid, and we don't think about that much about what do people do with that electricity. This is such a different product that we really do need to have a much better understanding of different use cases and limitations even of the technology that may exist. Some of the markets we see, remote mining for sure. We've been talking a lot in Canada with some remote mining applications. We know there's a few in Alaska as well that could potentially benefit. But some of the cost of diesel for these remote mine locations is just extraordinarily high. So we see pretty strong potential market for us there. We could also supply all of the heat for those mining operations. Industrial process heat, so our outlet temperature, if we just want to provide nothing but heat, can be in the range of 1,500 degrees Fahrenheit, plus or minus about 100 degrees. So, even some industries that are using natural gas, which might be pretty low cost, the volumes you need to get to that type of temperature are actually pretty high. So that's where we're interested in, some of the industrial processing potential for the technology, because, even if we're competing against what's generally thought of as a low cost fuel, to get to those really high temperatures is challenging, or at least requires a lot of volume, which the cost is maybe not as cheap as it would appear at first. District heating for sure, we see that where there may be some applications where we provide nothing but district heat, but we can also capture about 7 megawatts thermal just from our power conversion system waste heat. So where we can capture that additional thermal energy for district heating, it really is a big value boost to the product. Then remote communities are really a combination of electricity, district heating, infrastructure installations, critical, like Air Force bases, military bases. We can certainly provide a completely off-grid solution for energy at those types of facilities. We can greatly limit the need of transportation to those facilities to continue to provide energy, which really could add some value to DoD facilities. Disaster relief. We've been talking a bit with some folks in Puerto Rico around even the capability of this type of technology to support, post-disaster energy. We can't just, and I'll talk a little bit about our deployment methodology. We can't just bring a reactor and have it connected in 2 days or something like that. So it's not exactly an easy, quick disaster relief scenario, but if we have an installed base of eVincis in Puerto Rico, for instance, that's also supported by renewables in a microgrid, if a hurricane would come through and knock out the renewables, which is a very plausible scenario, we can bring more eVincis to the existing installed base and get them connected quite quickly. So within a less than 1 month time, we can actually add capacity if there's an existing install base. And, a month sounds like a long time for disaster relief, but, Hurricane Maria is not too long ago, and it was many, many months before they were really even in a reasonable state of restoring generation capacity. Research reactors, we're looking at, the US and Canadian research reactor fleet is very, very old at this point. They're kind of even limited in what types of research can be done just based upon the way those old research reactors have been designed. We see a pretty good fit of our technology to serve really a three-use scenario at some universities of being able to provide electricity, the district heating for the university, as well as adding value from being able to perform radiation type research on materials and isotopes and things like that as well. And then hydrogen generation's up there because we've really been looking at the ability to create hydrogen and then also subsequently from that hydrogen ammonia to be able to decentralize the production of those types of fuels for when we look out into the future. Those are other ways to reduce carbon emissions from vehicles and boats and other things that might not be easily converted to battery technology, or in really cold areas, battery technology might not, even be a feasible solution. And the high outlet temperatures we have actually support a much more efficient hydrogen generation process. There's some companies out there now that are doing solid oxide electrolysis that need, 1300 to 1600 degree Fahrenheit temperatures to run their processes, but it's 2 to 3 times more efficient to generate hydrogen versus low temperature electrolysis. And then decentralizing that production also really supports the ability to not have to store large volumes of hydrogen, which is a challenge and very expensive, or transport hydrogen, which is also a challenge and very expensive. So we do see the technology playing in a real key role in a future hydrogen or ammonia type energy economy.
Before we move off, are there any questions? Okay, I did just do a quick look to see what you could do with 1500 degrees Fahrenheit. So yeah.
Yeah, we can do a lot of things, which is, honestly, we haven't thought of probably half of them, or not even maybe 10% of them, I would say.
I have a question. This technology has been around for a while. You're, of course, improving on it, but I can see a real need for your small power generation plants in the Arctic, kind of Russia, Alaska, and energy is a big problem. And of course, with the concerns about climate change and all that stuff, I kind of wonder, at this stage of the game, it's probably very expensive to produce these plants. And I was wondering, when do you feel you'll be able to get to the point where you can produce them at a lower cost, which would make it competitive with other sources of energy?
Well, you mentioned costing and pricing, so you're going to be covering that a little.
Yeah, I'll talk a little bit about that, but I can answer.
No, we'll wait.
Yeah, some of it now.
Is that okay, Roger?
Yeah. Oh, sure.
Yeah.
Oh,
Related to that, I was wondering, kind of market size for the research reactors. Seems like there wouldn't be too many.
No, not too many, but in the tens in both Canada and the United States is not out of the question, right? So, even in our discussion yesterday at UAF, there was some comments about, well, how many do you really need to get to reasonable production scale? And, it's not hundreds, and it's not 5, right? It's somewhere in the 10s, 20s, 30s reactor. We can start to see now we can get a path to really getting to production scale, bring the cost down, right? So even research reactors, if they play a number of 10, even 5 in Canada, 5 in the US, it starts to get you to, you can start to climb up the scaling hill and start to really come down the cost curve from a scale perspective. So that's why we're interested there. Yeah, not huge, but we don't need hundreds either, right? At least not right away. Go ahead. Oh, key piece of why is this technology different than any small modular reactor or even micro reactor that people are talking about out there right now is right here. Basically, there's a scale of what does small modular reactor mean? And it's kind of, there's really big ones that they're really not that modular, and they're pretty big construction sites. And then there's micro reactors, and we're trying to be even the farthest to the small size, even in the micro reactor side, because we think it's important for a lot of reasons. So basically, our plant, the whole plant, is 4 containers, 40 feet by 14 by 14 containers. One for the reactor, one for the power conversion unit, one for the instrument and controls cabinets. And then another just that's kind of ambiguous, but it'll be tailored to what the use case is. Mm-hmm. So for district heating, we might need an additional small heat exchanger. For off-grid and black start capability, we might need a capacitor bank or some sort of hybrid battery and capacitor bank. Every application is going to need a little bit different support equipment, but again, nothing in massive sizes. So we see that the key here is transportability via truck, rail, or barge or other ocean-going vessel to get to those truly remote areas. Others have technologies that are modular, but even one of our micro-reactor competitors is more like 180 truckloads from what our understanding is. And 180 truckloads at a construction site and a remote site, right? That's going to be very challenging in our opinion. So that we're going far to the side of minimize construction, minimize actual shipping volume, because we think from a cost perspective to really get deployed in remote areas, that's the critical piece of this whole equation. It allows us to scale. So if a mine site, for instance, and some in Canada, some mine sites are very level power generation needs. Some, a junior mine turns into a larger operation and their needs scale up over time. And then some, as their ore starts to deplete, then their power use starts to come down. And we can meet that by bringing more of these or taking some away versus other technologies. Big fixed installations are going to have to meet whatever the peak demand is going to be, and then they're going to end up with a lot of underutilized capacity if that demand starts to drop down.
Yeah, would any of these units be transportable by aircraft?
So yeah, aircraft is a big challenge for several reasons. The maximum possible accident in aircraft transport is so much more severe just from a loading perspective of an aircraft crash, right? It becomes extremely difficult for us to kind of get our heads around from a regulatory perspective. How can we get through that? From a DoD side, that's a bit of a different story, right? They're more comfortable working in the worlds of shipping or even putting nuclear weapons on planes and things like that. So DoD is a little different. For the commercial world, from regulations, we see that's a very difficult road to plow. But actually at UAF, we were talking that there was some Kinross guys there, and they said they're actually looking at low speed low altitude, like really low altitude, blimp type
Right.
transport. And then that was one of the things, we didn't know that.
Like
We had
hover-
never even
just
thought of
hovers
that.
and-
We had never thought of that, right? So, that type of technology might actually allow us to be able to minimize that maximum possible accident during transport for, floating type application. So, literally hadn't thought of that or even knew that was something we could think about until yesterday. So again, that's kind of why we're here, right?
Yeah.
There's all sorts of good ideas flying around, and it's been enlightening for us.
Now, we've looked at this for quite a few years, how are we going to develop our more remote locations? And, that we have discussed the use of blips or
We have a number of places that
where
the
there's a
fastest way to
will,
get there is
there's
a plane.
a way. And
or maybe
Yeah.
the only way to get there.
Yeah.
We do have a question here in the
Mhm.
chat box. Looking at data, you can read it. Looking at data
Yep.
from November 2020, it shows Westinghouse, eVinci, and X Energy, XE Mobile as are
Yep.
under current PELE listed.
Yep. Yeah, so the PELE program was a DoD program run by the Strategic Capabilities Office, the SCO, to support development of a transportable micro-reactor. We were probably the only technology because the other competitors are gas reactors, they're bigger. So we were probably the only technology that could meet the original intent of the PELE program, which was truly almost like a truck mounted type application. But PELE evolved a bit to allow for larger scale reactors. And they also moved to a decision based upon technological readiness level of gas reactors being higher than heat pipe reactors. So Westinghouse was not selected to continue in the PELE program. But the PELE program kind of morphed into a medium-sized semi-transportable reactor, for which when we actually look at the DoD market, and this is all our opinion, but it's what we truly think inside of Westinghouse, the PELE program is developing a reactor that's not quite as transportable as what the Army and some other folks would want.
right.
And it's not large enough to support a lot of the actual, 20, 30, 40, 50 megawatt size demands of fixed bases. So, we're kind of confused now because we thought, hey, we're going to make the smallest, most dense power reactor, we're going to win PELE, no problem. But then they kind of opened it up to be bigger, which didn't help us because we're probably the only ones that can get to that tiny, tiny size. So, they're kind of making this 1.5-ish megawatt technology now that, you could literally need 20 of these or 30 of them for some bases. And then you still can't put it just on a single truck or a plane to transport it. So we got kind of confused as to what the aim of PELE ended up being. We weren't down selected, which honestly freed us up to be able to do what we think is the more economical, the bigger 5 megawatt. And now we're working with some others in DoD about if you really want a truck mounted reactor or one that you can fly in a C-130, the only way you're getting down to that size is a heat pipe reactor, which is what we're doing. So, long story short, we think PELE maybe didn't quite hit the mark on what the actual market is. And, it's allowing us to kind of go in a different direction.
They were looking at putting a nuclear reactor in Galeta. Now, I don't know
Yep.
whatever happened with that project.
Yep.
There was a lot of talk about it, but are you familiar?
I am. The Tosha before us was the plan. That was about a 10 megawatt electric, so it was much bigger than the capacity or the demands for Galena. But I've actually talked to Marvin Yoder, who was one of the project leads for the Galena project. And I have a discussion set up actually for next week to talk with the lead, the project leader from Toshiba, who actually used to own Westinghouse. So we still communicate with Toshiba to get just a better understanding about what were some of the challenges and also the opportunity of putting the Toshiba 4S at Galeta. But Toshiba basically they decided not to go through the US NRC regulatory process, which kind of stopped the whole project.
Regarding what we're seeing on the screen, you talk about scalability. How much of what we're seeing, again, 4 trucks to put in the initial unit, if I needed more power, 5 more megawatts, would I need 4 more?
Yep.
Or are some of these able to accommodate?
The instrument controls can potentially do more than 1 reactor, but I think a good assumption is probably 4 more at a time. But if one is providing all the ancillary services like district heating and all those other things, you might not need the 4th container. Right. So there's a million little kind of scenario thoughts, but yeah, I would kind of in your head just think 4 at a time. But we might be able to optimize depending on.
Back to that Galena question, has the regulatory landscape changed a little bit? Or I thought there was some update to that a couple years ago. Or
yeah, the regulators in both Canada and the US have really now understood, and they haven't quite jumped off the ledge yet, but I think they're much more understanding of the regulations as they exist for a large pressurized water reactor or a boiling water reactor just they're not going to be appropriate for microreactors. So that was a key acknowledgement to get, like, you can't put a 200-person security force on top of a 5 megawatt reactor, and nor do you need it, because this is much more like a research reactor, right? So some of the discussions we're having are, just to use security as an example, is, research reactors in universities are very similar size. You could actually make an argument, you could damage or destroy the reactor if you had a bad actor get to a research reactor even easier than this technology. And those campuses rely purely on local law enforcement response, right? So there are some real technical and just logical arguments that we can work with the NRC and CNSC to say, this is more like that research side. And they're open to those discussions. And they do allow for exceptions, justified exceptions to all current regulations. That doesn't mean they're going to agree with them, but you can put your approach forward as why I do not think this applies, or I do not think this applies exactly in this way, and here's how I meet it with my technology. So there's nothing in US or Canada that's physically stopping these from being licensed, other than getting kind of the mindset of and comfort of this exception is acceptable. Because certainly you can't go through part 52 or 50 with no exceptions. This is impossible.
You say that Westinghouse is probably ahead of everybody else in the curve of producing these microreactors. So how long, in your opinion, would it be before one is deployed in the United States?
So our deployment timeline we see is late 26, early 27. And we see that substantially driven, if not completely driven, by what we see as a reasonable time frame for the regulator. We told everybody yesterday, I think Mike said it, but I'll say it now too. Anybody that thinks they're going to get this licensed and deployed in any of their technologies next year or the year after that, I don't think that's even remotely reasonable. I think we got a 5 or so year effort working with the NRC, doing very detailed tests, right? Physical tests, right? There's others in this space that are trying to just convince the NRC everything's okay. I'm not that different, or here's my reasoning, and just doing it on paper. I don't know how effective that will be. So we're taking a much more typical approach of we're going to test and demonstrate almost everything along the way, and we're going to show it to you with our technical justification. We've done this test. We have more testing built into this program than either Mike or I would love, because it drives a lot of cost. But so trying to convince the regulator on paper without real hard evidence, I think, is difficult.
Right, so we do have a credible plan to get us to market, commercial market by 2027. 2027. PELE, which is through DoD, they use different, as you know, different licensing program under DoD program, and certainly they could get there. You could get there faster because the requirements are different. I'm not saying safer or not, there's just different requirements. So our focus here is how we can get this product to the commercial market. And we believe that the 2027 program is still aggressive for any nuclear technology developer. But we think it's realistic. You could get there. So
even PELE, though, if I remember correctly, they were a little bit vague on the time frame. It was kind of between 2020 and 2030, right?
Right. No, I mean, they have publications about 25,
25-ish, yeah.
26, but again, it depends. It's a different ball game. Really what we learned working with PELE with phase 1A, which we were in it, 3 companies were in it, we were one of the 3, is that it's just different requirements, different timeline, different needs, different applications. And now when you shift to commercial, yes, the fundamentals of your technology, like your safety case, will be somewhat similar, but everything else is just going to be different. So
one of the things that a lot of people are in a panic, around the world is cybersecurity. And, I don't know, your computers are involved, and sure, on operating one of these units, but I imagine that's something you'll be taking into consideration.
Yep. Yeah, we actually provide the hardware and software for cybersecurity to many of the global nuclear operating fleet plants right now. So, this is why, just Westinghouse, we believe we have the real capability to deliver something like this, because cybersecurity is a piece, instrument controls, actually manufacturing the components and the parts, right? The licensing. We have people that's what they do all day, every day for the existing plants, right? Some of the more startup type companies, that are going to go try to figure out, well, how do I keep my instrumentation and control system cyber secure? They're probably going to have to farm that out to an existing company like Westinghouse, honestly, because there's not a lot of people in the world that can provide that type of service. So, that piece of Westinghouse, even Mike and I don't know a lot of the details because it's kept very secure as to how we accomplish those things. But we have that capability internally.
yeah, absolutely. I mean, cybersecurity is something that we are very mindful of. But I can tell you though, that's what we talked about yesterday. Cybersecurity is a moving target. They get smarter. They get. I mean, it's on the news now about hacking everything. So you got to be very vigilant, especially in this industry. And the regulators, even though sometimes we butt heads because they'll ask us to do more, are extremely vigilant and about the requirements around your cybersecurity controls management, and it is evolving. So you got to stay at least half a step ahead of the ones getting smarter. So which is not, that what Mike is saying is we're in it, so we don't have to get in it in 2027. We're in it now with the operating plans. We've got to provide that kind of support. So in 2027, I bet you it'll be a completely different type cybersecurity control systems that you will use today, because you gotta evolve, and it evolves like your iPhone.
We literally have some rooms inside our headquarters where those guys do those types of things, and it's like no one can get in, right? So they're constantly monitoring and trying to, they're evaluating how are different networks being attacked even outside of Westinghouse and things, and they're designing our then system and updating it such that we can keep intrusions out of existing plants.
That's an absolutely valid concern that's on our minds as well as everybody else's, but we're in it, so we think we know that we'll be best positioned to make sure when we deploy this, because we are ultimately, if we deploy 10, 20, 30 of them, it doesn't make sense to operate them individually. Autonomous controls and monitoring is really the way to go, because it's a battery, it's going to run. It's the size of this room, it's going to let it run, and the less human interaction you have with this machine, the better off it's going to be, because we humans make mistakes. Yeah. So
You talked about in disaster relief of being able to bring in power generation or other type of energy production within a month, even if there is a kind of a receptacle system already in place. So you've got your 4 modules, you move them in place. You obviously have a substantial setup time to get it all hooked together and operating. One of the things I think, if you read the Arctic strategies for the military, which I think there's one written for the Navy, the Army, and the Air Force now, that they're going to move more towards a Arctic capability that probably is going to exist in Alaska and remain in Alaska, because we are America's Arctic. And they're not, it's probably not feasible for them to set up bases everywhere in Alaska, but my guess is they'll be able to move and set up bases quickly if necessary. I would, just to guess, I have no idea. I would say a month is not quickly. So have you thought about that end of the issue? And, and could I make this more of a plug and play type situation?
Yeah, so depending on the power output, right, and that's one of the things we're looking at for DoD is really continuing to go down the path of a truly truck-mounted, air transportable single container design. We can, our power output is probably going to be lower than a megawatt for that design, because there's only so much you can physically do, because a lot of the space you actually need for shielding. So the reactor gets pretty small to fit in that container. But that's our thought for the truck, Army truck mounted, that could also be used for rapid deployment. It's going to have to be smaller than this, but that's what we think is probably what the DoD really wants, is not a medium-sized reactor, but maybe a bigger one for, again, like the bases that aren't going anywhere, and then really small or quite small for fast deployment.
Yeah, so Jim, you're spot on in the sense that this application will not work, because that's not it's intended to, for a mine or a base, but the one thing we did learn, even working with PELE with the phase 1, is this technology, that's why we stuck with it, is fundamentally the physics are there to allow you to shrink it very, very easily.
That's good.
To shrink in size. And if you can just shrink it to where, let's say, 0.5 megawatt electric or 1 or less megawatt electric, you can fit it on one truck and you can control it and you can deploy it a lot faster. We just plug and play. But we felt from a commercial application, just to be honest here, will not be economical.
Mhm.
For military purpose, it's a different price. And
Money is less of an object.
yes,
Capability is valued.
capability, reliability, endurance is the requirement there, not the cost. But if you go to commercial, to your earlier point, you got to be cost effective.
Mhm.
And we think you got to be at that number as a minimum to be cost effective.
Yeah, like we struggle with, right, there's other competitors designs that are down in the, maybe 1.5, 2 megawatt range that are still fairly fixed large plants. And, we don't see the math ever working out on that, right?
I mean, your cost effectiveness is a function of how much
Value can you put out?
revenue you get. Revenue is a
Right.
function of your thermal heat and power output. And it's not that complicated.
Yeah.
So
I had happened to look at the clock. We're actually coming around the hour.
Mhm.
We're fine to stay.
Yeah.
And in fact, we're all supposed to meet after this anyway.
Yeah.
Do you want to zip through this presentation?
Yeah, I can zip
Or are we
through.
really
Yeah,
already-
let's just,
Well, this has been a really amazing
Yeah.
conversation. How are we doing online? Everybody okay? Everybody's wrapped. Okay.
Excellent. Keep going.
Okay. Thank you, Ms. Pease.
So, another key we see, just quick, right? No spent fuel or waste storage on site. We have about an 80-day cool down before we would remove the reactor for refueling. But we don't need to be offline for 80 days. I'll explain that real quick. Minimizes decommissioning because the actual construction around this thing is very minimal. There's no below grade installation. Our other microreactor competitors, at least that we see, are going below grade.
Oh, I thought I saw on the website there was something.
No, that's an ancient picture. That is an ancient picture. And hopefully it wasn't the Westinghouse website, but the DOE used that like 2 years ago. So it kind of got,
Okay.
that was one of
we
our,
made a requirement
Yeah.
for the engineers, no construction.
no, yep,
Below grade.
Remember, we deliver big plants, so we know what it takes to do construction.
yeah,
This is nuclear grade type construction. And doing those at remote locations is very expensive.
yeah,
Not to
Yes,
mention the
that's right.
practicality side.
yeah.
Okay, so I'm just glad I got.
Yeah, no, you're right.
It's a broadcast.
Great.
Okay, good.
Great comment. So yeah, nothing below grade. I tell the story all the time, but when I was delivering all the material to the AP1000 sites, I never lost sleep about the nuclear equipment. We delivered that without a hitch. I lost lots of nights of sleep trying to figure out how to get another piece of rebar that got damaged on site, get another cable that got damaged on site. And in a remote area where you might have a 2 or 3 month construction window, you damage a few pieces of this nuclear safety related rebar that needs to go down in the hole, you could miss your whole year. You're done, right? And these other guys that are going underground are going to need probably nuclear safety related rebar, nuclear safety related concrete. They're going to need all sorts of safety related construction materials that I just don't understand how that is going to be able to be done. We struggled to keep that flow going in Georgia, which was about 150 miles away from our nuclear safety related rebar factory, of which there's only like a couple on Earth. So, I mean, there's challenges like that that are important to really look at that construction side, because that's where nuclear can fail and fail pretty quickly. So we've eliminated safety related construction, all above ground, and our total footprint, on the lower left, is for a single unit site is less than an acre. And a single unit site for something where we know we need to provide continuous energy, our single unit site would actually have 2 bays. So when the reactor starts to near its refueling time, we bring in another into the second bay, get it fully prepared and connected to operate, and then we swap it over.
Is there downtime?
Extraordinarily low, but we'll probably need, few hours of downtime to perform the actual swap. But every scenario is a little different too, where, if it's a 10 unit site, we could probably do rolling wave kind of replacement and kind of take advantage of little lulls in demand. Even maybe a 4 unit site, you can do that type of situation in some places. everyone's going to be a little different, but I highlighted that one unit because we can provide basically almost zero downtime, even though we need about 80 days for cooling for refuel. But you know, building's basically prefab steel type building, concrete pad, not complicated.
And the thinking is you really, I mean, you deploy this to a site that you're just like a mine that's starting off. So the infrastructure is there. You just tell them, hey, I want one of those buildings to store this, the reactor in it as you run it. So it should not be, we don't envision this to be, you only go there to build that for your power production. If you have a diesel generator, you got to house it somehow, right? So it's not, what we're saying, it's not unique to the eVinci, and this cost would be required no matter what power source you use.
I do think we can take advantage of a lot of existing buildings, right? So if there is an existing building, you know, we don't see a lot of difficulty, you know, as long as there's physical size is, you know, big enough, which we think most diesel generators have similar size buildings. We could probably take advantage of existing facilities. What can we do with it? I won't hit on this much, just we can make heat, high temperature, we can make electricity plus district, we can pair with renewables because of the load following. We actually were talking yesterday with Golden Valley about an ideal application might be a regulation application paired with wind with Golden Valley or other utilities where we can actually enable renewables that have the problem of intermittency. So when we talk about costs, you know, one of our thoughts is actually enabling very low cost renewables with a bit of a higher cost, you know, nuclear side technology. We're not going to pretend that we're going to be extremely low cost on eVinci, but the total average cost, if you can enable those really low cost renewables, might actually be, you know, quite compelling. So that's one of the things we're looking at. So we maybe can get into maybe different markets than just the completely remote or military applications.
So when you talk about costs being quite compelling, of course, you know, that's all over the place, right? Yes. Yeah. So you talked a while ago about, you know, getting the production up to, you know, let's just say 50 or something. I don't know, but give me your guess where it might reach, because the last time there was somebody in Fairbanks talking about deploying, you know, small scale nuclear here. They were talking 40 cents a kilowatt hour. So, you know, to me, when I heard that, I thought, you know, well, so we're spinning a lot of wheels here to get nowhere. What do you think?
We think our first of a kind units will be in the range of 20 to 30. And that's first of a kind units, right? We don't like to try to project where will you be 30 units from now, because I feel like that's a bit disingenuous. There's too many assumptions. It gets a little bit kind of, but we see first of a kind, we can enter the market and be cheaper than diesel in the areas where they're truly off grid and it's being transported. Now, obviously, we believe if we start to get down the cost curve and to get scaled, then we can do a lot of things. But we think first of a kind is 20 to 30.
But yeah, one thing, Jim, we'll talk with you about here separately is that cost has everything in it. LCOE, right? Has everything. Security, your operator, your initial construction costs, even though you know you need it for anyone, yeah. But so it has everything in it. And if you know, for Alaska, one thing we learned yesterday is if we look at military bases as potentially a way, if there's a win-win solutions there to the community as well as to these bases, that number will go down because a lot of these things are already inherent costs at those bases. You don't add them in as if you do it at a commercial. But something we need to maybe chat with you a little bit more, and maybe you can help us better understand it, because we may have a paradigm here that may or may not be accurate.
Mhm.
Yeah.
Well, that's why I asked for your guess, because
Yeah.
I knew you can't put a stamp on it.
Yeah. And ours is, I think the higher power output helps with that LCOE as well. If I'm guessing, I would guess who said that, but safety, many layers of safety on this, multiple active reactivity controls, no operator action required. We have a passive core cooling jacket that'll keep the reactor lower than failure temperatures of equipment simply through airflow. So we could talk about this for months, but I'll kind of go quickly unless someone has
We
a
got a
question.
few. We do have a few questions on the screen.
Oh, okay, I couldn't see him.
Here we go. So the first question is 2 questions. Can I assume this project is still in the conceptual stage, or do you have a tangible?
I think so it's interesting. There's parts of the technology, because we've been busy building and testing things, they're actually probably far past the conceptual stage. There are pieces of the technology about core optimizations and things like that we're actually trying to get input from the potential user base so that we can finish the conceptual stage. So we're kind of across the spectrum, depending on what specific thing of our design we're talking about. But as far as the full package and its total performance characteristics, we're still in conceptual, but mostly because we're trying to figure out how to tweak things to best meet the biggest possible market, which is actually one of the reasons why Mike and I are here. So we're planning to be fully out of conceptual, across everything in September of this year.
Oh,
So that's why we need input so quickly, because we're kind of running out of time to make a decision of that might be important.
On the question list, Harold and Mary Ann are down in the Anchorage area. One of the questions is there going to be any presentations elsewhere at Alaska?
We're going to be in Anchorage tomorrow and Thursday. I can check the agenda real quick of where all we're going to be. But
So you don't know if you're going to have any presentations down there?
we're going to
We are, but there's established meetings.
Yeah,
so
they're
yeah.
established meetings. Governor's office.
On Thursday is the governor's office, I think. I
Yeah.
don't know who else is going to be there.
Meeting with Launch Alaska on 3 p.m. We're meeting with AVEC Thursday morning, Shugosh Wednesday morning, and a tribal community on Wednesday afternoon.
so that would be the closest to a public presentation of that last one.
Yeah, probably the launch. Well, the tribal community is actually not going to be public.
Okay. Yeah, it looks like this is it, Harold.
Well, there might be a chance, Harold, if you have some time, you can put together a forum. There might be some time in your schedule.
Yeah. So it would be tight probably, but it might not be impossible.
But also, I mean, certainly this is our first trip here. And when the world opened up, that's what I wanted to do, come here but it doesn't mean, this is, I guess all I'm saying, if there is a desire to have more discussions, we're absolutely open to it.
Okay.
We can do it through Teams, Zoom meetings. It does, if it doesn't work out this week.
I can come back.
Yeah. He wants to go back and go fishing. So.
Yeah. I mean,
7 seasons wrapping up.
yeah,
I know.
Fishing is far more important to me than any professional pursuit.
We really appreciate you all making yourselves available in this way.
In my opinion, and one of the reasons we call this program Energy for All Alaska is Alaska has been challenged by the cost of energy forever and continues to be today. So, just a number of issues, our inability to diversify our economy.
Yep.
All of that, in my opinion, focuses around energy. So, yeah, I think, very interested, obviously 2027, ways out, but, there's going to be people still concerned about the cost of energy in Alaska in 2027. So, yeah, good stuff. Harold or Mary Ann, you want to weigh in on any opportunity for additional presentations in Anchorage?
Well, I would like to weigh in and invite the team to present to the Commonwealth North Energy Action Coalition. And we have meetings on Fridays at the noon time frame. And boy, oh boy, this would be a great presentation to get out there. with our public policy think tank.
Marianne, will you go ahead and post your contact information just really quick so you can have your email?
Yeah, we'll.
Absolutely, I'll do it now.
Yeah.
Should I do it in the chat?
Yeah,
Yeah.
sure.
Just, yeah,
Okay.
we'll connect with you here offline and see what we can do. We were planning on taking the red eye back on Thursday night, but let's talk offline and see what we can do.
Yeah. That probably means I get to stay next week. But we'll see about that.
Who's in charge?
Yeah. He is. So
I work for Aaron.
So she did have a follow-up question regarding cost per.
yeah. So
Everything you said right now, we're thinking in somewhere the
20 to 30.
range.
Yep. And
Currently, we pay 20-ish.
Mhm.
That's all in. So that's cost of fuel plus operations.
Yeah, that ours is as well, all in everything.
You figured 20 to 30, and figure your costs for energy, you have to consider 5 years down the line, replacing it with another unit.
Yeah, we have that completely built in.
Oh, you have it built in.
Mhm. We've done our entire,
Okay.
all our refurbishment costs, which is not that much, but all of our operational, all of our fuel for refueling. We have the back end decommissioning costs. We got it all in there.
Good.
But think of Golden Valley, who you talked to yesterday apparently.
Mhm.
So we have, we pay, let's just say 21 cents a kilowatt hour. A large portion of that is distribution.
Mhm.
We're talking production here.
Sure.
And you're, 20 to 30. So your production is pretty high for a community. And I get it's micro scale, but nevertheless, keep in mind, I don't know where we're going to be in 10 years, but
That's true, Jim. But these are the things we've got to look at, because I mean, think what we envision is this is a microgrid level, meaning I don't need the centralized distribution system. We're talking, Mike and I are talking to Lord Norman Foster from the UK. I didn't know who he was, but he's a major architect, and he's all of a sudden is really interested in decarbonizing and supporting decarbonization with his, charity organization. He's the one who designed that egg-shaped building in London. I don't know if you've seen
the Apple campus as well. And
Apple. Yeah. So many famous architects that he's done, and he has a new passion to be part. One of the things he's looking at is, he says, Mike, you guys are looking at it wrong. This is not just for a mine. He says, we're building in the world a Manhattan every day or every week.
Yeah, it's like
Manhattan-sized city. So, and the biggest cost of your energy is your distribution, because you have to centralize things. Look at Texas. What happened? He used that as an. He said, if you go with eVinci type micro-reactor and you're powering that city locally and not having to worry about running distribution lines across, many miles or kilometers, it's a huge, not only cost saving, but it's a huge benefit to the environment that you're not running all these distributions. So transmission. So these are the kind of, so you're right. So we got to look at the total picture, but our analysis has been more working with mines in Northern Canada and looking at their localized grid system and on the localized distribution. So we went to Aurora yesterday to the coal plant here, and the heat and and that's, we think that would be a great. I mean, I got really excited by the end of sleep last night, thinking that's if that decommissions by end of the 20th, 2027, 28 or 30, having a clean energy source for the city of Fairbanks to give heat as well as to give electricity, because if we're the right size, it's they're 12 megawatt thermal.
Yeah. So
we're about 15 megawatt thermal.
Yeah.
It's important to mention, which Mike should probably fire me because I didn't. The 20 to 30 is we're not capturing any of the waste heat.
This is just electricity.
So that's purely electricity.
The thing up here is what
Capturing the heat, the effective then total energy value gets a lot more interesting
Yeah,
than 20 to 30 cents for purely electricity. And the Aurora, we actually, they gave us at least some high level numbers as to how much they get paid for the BTUs. And it's actually pretty similar to what they're getting paid for the electricity. And we can basically provide almost their total BTUs through our waste heat without any real additional cost. So that's also important.
Well, you know, I think besides distribution of electric lines, you know, that probably needs to be modernized. The distribution of heat needs to be modernized, because several years ago, this town did a study on, you know, could we expand the heat distribution system? And, you know, even though, you know, they're putting out excess power, there is not being heat, it's not being consumed. It was too expensive to just, you know, put in the utilidors or whatever is needed. And I don't know if that can be modernized or not, but, you know, it might be worth it.
Mr. Atkins, I see that you're off of mute. Do you have a question?
Yes. The application of this type of energy is particularly important to Alaska, because the villages that you know we're sort of responsible for, you know, they have to be brought along with any development in Alaska, and doing that is you know, they're getting more and more, so they depend on electricity and heat, and so it's really important. But one of the things that it seems to me like that Westinghouse needs to do is to sort of change from the technology of light water reactor vocabulary that was developed in 1945 and on, that we still use today, which carries with it the angst of the normal citizen about the problems with nuclear. In other words, we call this nuclear when it's so much different than the light water reactor that we probably should be calling it something else, not to deceive anybody, but to help the transition from this type of technology into society. If you try to put this reactor in Galeta, say, where they have an airport that you can transport it to, the big reaction is going to be that you haven't sort of made the difference between this technology and what's the 2,500 pound pressure that you need for light water reactors. There's just seems to me like whether it's this one or some molten salt reactor, the terminology needs to be changed a little bit. Also, you know, we really haven't talked about what's the basic safety in the heat pipe technology. And I really pay a lot of attention to what's online. And of course, some of it isn't true, some of it is. But the thing is, I really haven't seen much from Westinghouse in explaining this in detail online. Then the next thing is the waste products from this heat pipe technology. Is that close to being available for a bomb? In other words, there's U-233 waste in there of some kind. Can that be converted to plutonium very easy? That needs to be explained so that you know, the security in a village with one operator is not very good. And so it all sounds good, but we know that one of the things that happens with technology like this is the bad people catch on real quick. And so we want to be ahead of that. And we want to know that everybody knows that that's not a possibility, that some terrorist would go to one of these small reactors and try to steal the waste.
More likely up here, I mean, we did have some Yahoo put a rifle round through the Trans-Alaska pipeline.
Yeah.
We have Yahoos.
Yeah. So I think great comments. So when we've been thinking about the same of the verbiage, you know, and we haven't quite settled on what's quite the right way. I think your comment's exactly correct, though. To not be disingenuous that yes, this is a nuclear technology, but it is very different than any existing large nuclear plant, right? This slide here maybe explains a little bit about the heat pipes, but there is no pressure, right? It's basically this is an atmospheric pressure reactor. The waste is only TRISO fuel. So there's no sodium waste. The sodium is completely encapsulated within the heat pipes. So the sodium never touches the fuel. The fuel is completely encapsulated in silicon carbide and other layers, literally to the point where, from a proliferation perspective, it's almost impossible to reprocess TRISO fuel, because breaking open the capsule for the actually very small uranium kernel that's inside is almost impossible physically to do. That's one of the reasons why TRISO is a bit of a preferred fuel from the regulator and the IAEA right now, is because it's not really able to be harvested for weapons use. Now, one of the downsides of it literally is reprocessing is almost impossible. So literally there's been thought of what happens if TRISO fuel container breaks, even when we're just shipping the pure fuel and stuff lands on the road. It's like, well, you pick it up. It's all, even if somebody could pick it up and get it, to literally crack that thing open requires mechanical forces that are like extremely high. So there actually has been a lot. It's something we can communicate better about, for sure, about the proliferation resistance of TRISO fuel. But I think you got some really good comments, Ross. And we haven't been publicly advertising as much as we will be soon. I think one of our thoughts is we wanted to be very sure we could deliver this technology versus going out and telling the world, hey, we got a thing, we're going to make it tomorrow and it's going to be great. We've been really sitting and doing this type of thing, which is actually making the piece parts and components, heat pipes, prototypical cell of our reactor core, the primary heat exchanger, and actually doing real testing on our pieces and parts. So we're just about to embark on the phase of, we're going to start doing more things publicly and even on just websites and things like that, of we're ready to go do this. I think others, some are taking an approach of just saying they're ready to do everything, and they don't have this. They don't have.
I've been seeing too many of those recently.
Yeah, you don't have silicon carbide, fuel, actual pellets made yet. We have made, with a supplier of ours, made actual TRISO compacts. This test is just 3 weeks ago, where we were running this up to our prototypical temperatures with 7 heat pipes in a cell of the reactor. We validated all of our codes and analyses. We're basically spot on for the temperature dispersion throughout the core of this thing. We got how much heat can our primary heat exchanger actually capture, so we know exactly what our efficiencies are going to be. We're doing the real stuff, right? And we rather would do that to say, like, oh, in case there's a problem, we don't want to be out telling the whole world, look how great everything is. And we'd rather get past a few of these, and that's where we are right now.
We have someone, phone number 907-9826. Yeah, here we go. 907-982-6931. You're off mute. Do you have a question?
No question.
Oh, okay.
But Slide-wise, that's pretty much what I have, unless, I could go back to the heat pipe slide if, anybody's really interested on how the heat pipes work. But that slides-wise is about what I have.
I was gonna ask you about that last picture there. One forward where you're actually looking at the test apparatus.
Yeah.
So how many sides is that? Pentagon?
Hexagon.
Is that hexagon.
Mhm.
Is that the actual fuel rods in there?
No, so
Okay.
this is without fuel.
Okay.
Those are with the heat pipes. There's 7 heat pipes loaded. So that hexagon is a cell of our core, right? The total core is a bunch of the hexagons,
Okay.
but that they really just kind of stack together,
Okay.
right? So there's 7 heat pipes in each cell. And then what we did was simulate the fuel with ceramic heaters, electric heaters.
Plug them in.
Yeah.
Okay.
And we actually plan to run this same type of test at the US National Labs starting in late 22 for a period of, a handful of months into 23 with the actual fuel. And these are things that we think before you can really, be sure you can get through the licensing process, you have to have a plan and how you're going to do all these tests. Which is what gives us confidence we can actually get through the regulatory process.
So the fuel would actually, or the reactions take.
Yeah, the fuel's going in those empty holes,
Okay, yeah.
basically. Yeah, and actually a few of those empty holes will also have control rods.
Okay.
So there's a combination of the empty holes would have control rods and fuel.
So each heat pipe is a heat exchanger, really. I mean,
Mhm.
one side will be where the fuel will be in a different hole. And it heats out one side, and the other side where your heat exchanger will takes the heat out of
Okay.
it. And that thing goes a very, very high speed inside the heat pipe where, it goes back, gets condensated, it gets colder, goes back into the hot area. It's just
Yeah.
basic capillary physics that makes it happen.
Yeah.
What you mentioned early in your presentation that your nuclear reactor works better in cold temperatures.
Well, the reactor doesn't, the power conversion system does. It's the same as a big plant where if your cooling water coming in is really cold, like the same nuclear plant in with a cold water intake versus in Saudi Arabia or something it's much more efficient. So it's similar with our power conversion
It's the
system.
delta temperature
Yeah.
on your heat exchanger, right? The core temperature doesn't change.
Yeah.
But
Core will be the same.
that ambient temperature, because it is taking air from the ambient. If your air is a lot cooler and your temperature coming in from the reactor is hotter, you get more power out of it.
Mhm.
Yeah.
But that heat pipe in the lower right, that's a Westinghouse made heat pipe operating at 800 degrees C, where we did that for 120 days and it worked like magic.
So that gray metal pipe
That's a
looks like,
heater.
oh, wow.
Yeah,
Looks
that's
like a
cool
neon
heater.
bulb, yeah.
Yeah, the
Neon
heat
bulb.
pipe is the horizontal in that picture.
And
And
coil is the heater, and
Yeah.
you go up to 900 degrees Celsius or 850 Celsius.
Yeah.
So
That hot.
and-
yeah.
And there's others that have quote unquote are saying they have a heat pipe reactor, but we actually looked at the global nuclear supply base to see if anyone was able to make a safety related heat pipe, and we found 0 people that were even close. So we were making our own heat
Made our
pipes. And at nuclear safety related quality grades. So, again, it's, this is one of those things.
You didn't have any outside orders yet.
Yeah. People can say that they can, hey, I got a heat pipe on paper, it'll do all this stuff. And it's like, well, we actually have a heat pipe in real life that does all this stuff.
We're not sure we sell it. We give it to national labs.
Yeah, we're providing some to the labs.
We did have a question here regarding the national lab. You mentioned that testing at a national lab. Is that Cynthia?
No, well, we do a little bit with the testing with this test with nuclear fuel. We're going to do some testing at Los Alamos and some testing at Idaho National.
Oh, Idaho National.
And then our plan is after that test, we really start to move towards building a full-size reactor. And we will test that most likely at Idaho National out in about 2025. And that's what, right after that, it's basically, we have all the testing we think we need to get full design certification and start delivering commercial units out in, late 26, 27.
Now, of course,
Yeah.
we're all hoping, well, certainly there are a number of us hoping that you'll do a real world test
Right.
after the lab test. There might end up being somewhere here in Fairbanks.
We hope so too.
We hope so too.
But what we're doing, I mean, this is not trivial because it is a battery, because you're dealing with 15 megawatt thermal, so it's not big. Our actual test unit is a truly commercial unit, but we're going to use that, so it's in essence, whatever we deploy in commercial space will be the same one that we use to test and certify the reactor. In the nuclear world, like to Ross's point, you've never done that before because you can't demonstrate 1,000 megawatt electric. It's a power plant. And in this area, we want to make sure our demonstration reactor or battery, I like changing the terminology thing because it is different, a lot different. It's really a paradigm shift too, is a full size. I'm not going to test a 500K kilowatt unit and say, okay, simulate this, upscale it. I'm going to test the whole thing. And that's what I told the team I want to do. Frankly, some of my engineers came back and said, are you sure you want to do this? You want to do this? I said, yes, can you do it? They said, okay. But their initial reaction is, let me do a smaller one. And I said, do you really, can you do the full one? Why would you want to go smaller? Because it's going to take you the same effort to do a 1 megawatt electric or 5 megawatt thermal and a 15. It's just the engineer's comfort level. So they are going a little bit outside their comfort level, but they feel they can do it. So.
What was the last picture?
Last picture, just kind of summaries.
Okay.
On there's other parts on the right too. We've made our control drums, we've made rods, we've made graphite core. We've actually made parts components. We have the ability to actually physically deliver, where I think others may or may not. Our opinion is probably most of them don't.
We're also biased ourselves.
Yeah. And but it also helps with the cost analysis, right? We have a pretty good idea of our component costs because we've actually done it, right? So we know how much the material costs. We know how much machining is. We know, because we've done it. And the timeline at the bottom, we kind of just talked through. It's do that similar test as what we showed with actual nuclear fuel kind of in the late 22 and into 23, because it's kind of a long duration test. And then you start really, getting everything up to full scale, build everything and send it to the lab for, plug in, let's go.
And the one thing, Jim, behind the schedule, it's not a given schedule. We know, it's the first thing I did with the team, these 100 engineers, said, I need a credible plan that you can develop that can take me to commercialization. What would that be? And they came up with detailed schedule, thousands of activities that will take us there. And I brought in the same people that actually have been dealing with the Georgia construction. So they're ones who developed, licensed by the NRC and deployed this AP1000 reactor. So the people with scars and bruises from doing that are the ones who put the plan. But I just want to make sure that we're also being transparent that it's a business, right? Can take hundreds of millions of dollars to do all this. Yes, we're getting some government support from the Department of Energy through grants, and we're applying for more. But the truth of the matter, and that's why we're here, is we got to start seeing potential for end users and others to think, okay, we like this, not just us falling in love with our technologies, because exactly. What's our market penetrations? We couldn't have done this 6 months ago because I wouldn't have had a schedule. I'm an engineer, so I can't sell unless I know I can do it. So so we put this together, and the key aspect of us being here and listening and learning is there really a true market penetration here for me to go back to my owner and the investors and say, you know what? Yes, let's put our next one online here. The market potential is there, and let's continue with that investment. And I don't want to make it sound binary and linear. We're going to make a decision, this is going to evolve over months. But my point of all this is, and we'll talk more privately, is what is the market potential? Mm-hmm. And that's going to drive what kind of a commitment the people with the pocketbook are willing to put into this kind of development.
One of the things that we hear talk about Alaska being an extraction state, so we're kind of mineral rich, but a kind of operation port. Not very many of those. We have Red Dog, which really, if you ever had an opportunity to visit a remote location mine operation, Red Dog would be the one I would suggest you go to. But one that's in the works today it is Donlin Creek. That
It's gonna be a big one.
the total research phase of Donlin Creek to get it from startup to operation. My understanding, and this might be dated, will be an investment of $6 billion before they put the first shovel of dirt into however they're going to mine it. They're not.
Is Donlin the graphite?
No, that's gold.
Okay.
It's gonna be one of the largest gold mines.
Okay.
They are not talking about shipping diesel up the Kuskokwim River. They're talking about building a pipeline from Cook Inlet into Donlin Creek. If you had any idea of the difficulty of building anything in Alaska, because regulators are just down our neck, and everybody thinks Alaska is their playground. So
Yeah.
we have really no capability to do anything without multiple opinions of people that have never been Alaska, never seen Alaska, doesn't have any idea really what Alaska is. But nevertheless, it's very, very expensive. Those type of operations, you won't really know what the market is until you get it on the market, because those type of operations would run to your technology in a heartbeat if it was available.
Yeah, there will be another mine up in Ambler. That's the, so that's something, that's on the drawing boards now. It's been a hassle. Every big mine is a hassle in this country.
The figure I've heard that 60% of the mining costs in Alaska are energy.
Right. Yeah.
Speaking of energy, there was one outstanding question from earlier in the presentation, and that's the change out and the change out time of the active portion of the battery.
Oh, for the refueling.
They talked about it when you were out of the room.
Yeah, so
It's 2 months, but not 2 months.
Oh yeah, so 80-day cool down, but we actually have a two for if you need continuous energy, we'd have a 2-bay building, and you bring the second in before the first
Goes out.
Yeah, goes out. So then
For it's depleted, it's still running.
Yeah, so then then you do this swap, which right now we think it's going to be a few hours to swap over because we'll have everything connected. It's just not operating yet. And then that one cools down 80 days. We take it back out on the truck that it came in on, only the reactor canister, back to a licensed facility where we remove fuel, or if it's been many years, we would cask store for decommissioning. And that time frame for how long that takes, we're actually starting to work on designing the kind of the process to do that, because we actually like to do that mostly automated, just from a radiological.
So we're not talking about say if you're relying on this power source, we are not talking about you have to be without power for 2 months.
We know that would never be
a few hours, maybe.
Which is the norm.
Yeah.
Right? A couple hours of downtime.
And the way we envision this, that's why we start these with kind of a salesy type slides about Westinghouse is our core business is services. What we do right now is we service operating plants, and our business and portfolio is based on that. So we don't really envision this as us selling a reactor and walking away, because frankly, we most likely not make money on the reactors we sell, on the batteries we sell. But where the business model does look attractive to us is because we're there for the lifetime of that operation, whether it's the technical support, the services. If you sell 2030 in Alaska, so what do? You build a factory in Alaska to refuel them, to get the new units out. You don't want to be building it in mainland US. It'd be too expensive. You can't maintain it. So that's where that's what we know.
I'm only smirking because I just bought printer ink.
More expensive.
Yeah, I know. I know where HP's making their money.
Right.
Amber will have a road to it. Donnelly Creek, you have the Yukon River and then has a road going to that too. So, you know, would they be able to handle the larger, well, they'd want a larger unit up there.
Yeah, you know, we're actually looking at, you know, one of the programs that we'll be starting, you know, this year is the more detailed design around the water shipment. Just what exact draft will we need and all those kind of considerations to, you know, kind of figure out what our limitations will be for water-based shipping. And that's another thing Westinghouse does, right? We, you know, when we do our AP1000, we actually go to all the ports where all the equipment's going to be moving through to make sure, you know, the vessel and there's enough depth and things like that to actually handle this equipment.
Big machines and
so
talk to the Corps, you know, Army engineers about flooding the river, raising the water high.
Yeah, we've done, you know, we moved all sorts of crazy things to all sorts of crazy places.
So if you're really interested in the Alaska market, you know, we have very few roads in Alaska, you know, very few railroads in Alaska. We do have substantial amount of rivers, you know, Kuskokwim, Yukon, you know, probably the major ones, but you know, you should really go to the operators that operate the barges on those rivers and understand what their maximum load and draft is, because that, you know, that's limitation. There's going to be no dredging of those, you know, of those rivers.
Yeah. And that's what our logistics team, you know, we don't do that all on our own. You know, we've looked at how to ship, you know, 900-ton pieces of equipment, you know, from one side of India to the other side of India. You know, we don't try to go in and figure it all out on our own. You know, we'll work with the local, you know, kind of shippers and transporters.
I'm sure we'll have some engineering challenges with the logistics, but I do know that we can work around it. And that's why because look, we're still in the business, right? I can't study everywhere.
There is another, pardon me, but there is another aspect of this type of technology that should be talked about at this time anyway. If this is going to be successful in Alaska, in villages, it's got to be cogeneration. And in that cogeneration, it should provide enough heat for a greenhouse, a year-round greenhouse. That type of combination of effort would be extremely beneficial and efficient here, whereas someplace else it might not be so beneficial. But the transport of food to the village is a very expensive thing. Now it's mostly done by air. And so to be able to grow year round, which that technology is already proven in Chena Hot Springs, with extra heat would make it even more economical. You know, you're talking about 20 to 30 cents, which is well within the range of what it costs now in the village. But with cogeneration, where it provides the heat and a greenhouse, it would be much more efficient and inexpensive. Now, in order for that to happen, there has to be close, I mean, right away, there would have to be close cooperation between whoever's going to supply the generation with some organization in the state, whether it be state or native. But I think talking about that at this time is really important.
We completely agree. One of our discussions in Anchorage with, you know, one of the indigenous communities, that's exactly what we want to take away is what are all the things, because they've thought about this, you know, what are all the things that you would do with that additional energy in both heat and electricity? And greenhouse was certainly right at the top of our list. We've gotten that same feedback in Canada. Galeta was looking at that as well, I know. But I'm excited to see, that there's probably a lot more things, and that we certainly haven't thought of. But the greenhouse, I think, certainly makes a lot of sense. And you could locate the greenhouse basically right next to this reactor, because we have the shielding in the building that you're not getting any radiation outside of that small, less than 1 acre building. So piping distances and things like that for district heating and electricity to a greenhouse, it's nothing. So we've even thought there's been some discussion around fish processing and even some things to enable kind of lower cost aquaculture, which I'm not going to say I'm know much about at all, but we're hoping to have some discussions like that of what are your processes, like what are some difficulties that you have from an energy and heat perspective in these various communities. I mean, that's what this is all about. I think it's what can you do with it? How does it help the community really solve some problems?
Sure, well, we better say goodbye to the people.
Yes.
I didn't want to be polite, sir. All right. Well, everyone, I normally would open it up for one last question, but again, we've gotten these guys for an extra hour. So I wanted to say thank you very much, Mike and Mike, for your presentation, Westinghouse and Micro-Nuclear. I'll be honest with you. Again, I've been watching these presentations now for the last couple of years. I have not been wowed. But this one's a little different. And so I very much appreciate this conversation.
Appreciate it.
All right, well, everybody, that's it. Next week, I don't know if he's still online. I believe we're supposed to have Gary Newman as our guest next week. He was going to give a presentation regarding, really the pre-GVA history of electric here in our community. But I will get that all confirmed up, and I'll, of course, be sending out the notices. Beyond that, again, I just hope everybody has a great week, and we will see you soon.
Very good.